Okay, so great. I started the recording. So today we continue our initiative of having guest lectures at the IGLU. So let me just tell you a couple of words about that. So the idea is actually to not just arrange the competition and make it successful, but also create potentially the community of people who are interested in particular problems that we're trying to solve here. So like it's embodied agents and specifically like understanding how can we build the agents who is able to understand natural language and maybe explain themselves in a natural language. So, and as a part of this activity, you have this mentorship program where you can go to Zoom, go to Slack and get some help from your mentors if you have a particular problem to solve, or maybe like just a question. And also I have the guest lectures, and today I'm happy to introduce Jianwei Yang, who's currently a senior researcher in deep learning group in Microsoft Research Redmond. And prior to that, he got his PhD at Georgia Institute of Technology, where he was supervised by Professor David Pari. And his research interests span computer vision, visual language, and robot learning. More specifically, his research focus is about structured visual understanding at different levels and further leveraging them for intellectual interactions with humans through language and environment through embodiment. And at most recent, he did a number of works on vision transformers towards various core vision problems. And now I will give floor to Jianwei, and like I also encourage some interaction. So like maybe we can like make it as following like I think the presentation would be for lecture would be for 45 minutes, but I think it's fine if we can if there's a question and we can stop the lecture, ask a question, or like we have a 15 minutes questions, 15 minutes per question after. And we can focus on obviously questions related to the presentation. But if you have a general question about IGLU by the end of this hour, so it's also a good time to ask. And now I will give the floor to Jianwei.
Okay. Yeah. Thanks for the nice introduction, Julia. So I'm very glad to be here to present our previous work in the domain of the embodiment and the natural language processing and the interaction between the visual agent and the in language and embodiment. So today I would like to share with you two works, and please feel free to interrupt me at any time in the middle of the presentation. So I would be very happy to discuss with you all about any problems. Yeah. So let's get started. So I would like to start the talk with a quote from Albert Einstein. So he previously said, "So I have no special talent. I'm only passionately curious." So I would like to highlight the curious or the curiosity. So as we all know, our humans has an instinct of the curiosity to know about our visual world. So when we are young, so if we do not recognize some, for example, animals, for example, a dog, then we probably ask the question to our parent, okay, what is this animal? So what is this and why it barks, something like that. So this is very natural instinct for our humans. And on the other hand, so if we cannot recognize something, we will probably, okay, move around the object and then capture different perspective, different viewpoint of the object to finally understand, oh, it's a dog or something like that. So this kind of curiosity instinct actually are born with us. But on the other hand, the robot does not have such a curiosity, even though we all know there is a robot on Mars called curiosity, but definitely it does not have any kind of curiosity instinct like our humans, right? So in this talk, I would like to further explore, okay, what kind of curiosity we can empower the robot so that it can also have such ability like our humans to ask the questions to human or explore in the environment to understand the visual world better. But the question is that the visual world actually is very complex. So as you may well know, there is a dataset called ImageNet. It contains 1,000 object categories in the daily life. So it contains over 1 million images. So as you can see here, there are a lot of different images and the appearance are very different. And this kind of images only contain usually one object in a single image. But even for a single image, actually, there are probably multiple objects inside the image. For example, as you can see here from the Microsoft, the COCO dataset, so there are multiple people, there are multiple objects in the images, and then the visual system needed to understand the whole image in terms of the object, in terms of the concept, and even the background, or even the scene inside the image. For example, the sky, the grass, the sea, etc. So this means that the visual system should be capable to do a lot of different understandings from different levels. So the single image level, the inside of the image, maybe the object level, etc. So the visual system needs to learn about different things, right? And even it becomes more complex if the visual system is inside a 3D environment, because as we know, so we are living in the 3D environment. So thus the agent should also live in the environment, in 3D environment, I mean. So basically, this kind of complexity brings a very big challenge to the visual system to understand its surroundings about the visual world. Unfortunately, most of the recent visual system actually is more like shown here. So give a bunch of different samples. So humans annotate all of the samples, and then a visual system, for example, use a convolutional neural network, or even the most current visual transformers to learn and classify different categories of the images or the content. But so this kind of visual system is passive. So it can only recognize the object categories we ask them to recognize, or we specify prior to training the model in a, for example, collected dataset. So ideally, we want to convert the visual system to a visual agent, like our humans. The visual agent can have the curiosity to ask questions to the humans. If it cannot understand some visual content, then it probably, ask questions to the human. So what's the color of the object? What's the attribute of the object? And what's the function of the object, etc. So on the other hand, the visual agent is living in a 3D environment. So it should be also able to have the curiosity to implore in the 3D environment to get a better understanding of their observations. So based on this motivation, so we have two works. The first work is called visual curiosity, which enabled the agent to ask questions to the human or oracle about the visual environment. And the second work is about embodied model recognition or embodied visual recognition. So the goal of this work is trying to enable the visual agent the ability to explore, to move around the object, to understand the object. So to summarize, these two kind of work is trying to achieve some sort of curiosity. Maybe it's not equivalent to the human curiosity, but still we want to push forward this kind of agent curiosity to help the agent to understand the world from different perspectives, from different methods. So the first work I would like to introduce is how we can enable the agent to learn visual curiosity through language. So this work was published at Coral 2018, so with a bunch of collaborators. And let's begin with these pictures. So let's assume that we buy a robot from Amazon, for example, and then we probably, start the robot and let the robot walk around in our apartment, and then probably it can recognize some object, for example, the table, the sofa, etc. But probably it can also cannot recognize some thing like this, like the candle, like the book, like the light, or etc. So this kind of new things actually are novel concept to the robot, to the agent. So what it can learn, or how we can do so that it can learn from this kind of new concept. So one of the way is that let's assume that, okay, it want to recognize this object. It want to know, okay, what this means. So probably there's a human like ourselves also live in the house, and then probably the agent can ask questions to us. Okay, what the orange object to the left of the television? So imagine, okay, the agent already know the television on the right side of the object, the green with the green box. So probably, okay, we can provide the answer. Okay, that's a candle. And the thing next, okay, it will probably ask another question. But before that, so to ask this question, the agent should understand, okay, it's orange color for that object, even though it does not recognize the category or the concept of the object. And also it needed to understand, okay, there is a television on the right side, and then the special relationship is, okay, so the candle or the object, the orange object is at the left of the television, etc. So that our humans can understand the question proposed by the agent. So the question is now it becomes, okay, how we can train an agent to ask questions about its surroundings to improve its visual understanding capacities. Here, the goal is more like, okay, extend the vocabulary size, extend the concept for the agent understanding. So the motivation to do this is that we first want to represent an image as a graph or as a scene graph. The scene graph contains the object, contains the relationship between the object and the scene graph, and even contains the attribute about each of the individual object, so that the agent can get what is known and what is unknown in images. And the second, the agent knows what's the relationship between the objects, so that it can generate some very good, non-ambiguous questions to the humans. And finally, the agent can relate unknown to known object in the image. So finally, let's assume, let's use this kind of illustration pipeline to show the scenario. So for example, giving an agent and the human, so probably we do not have the real human. Probably we have the oracle, but when the agent sees some image like this, probably it will ask, okay, what color is the forward most object or the front object? Then the oracle answer, okay, it's blue. It's blue. And then it will further ask more questions about the observations. And what shape is a blue metallic object, is a sphere, etc. So based on this multiple round of interaction between the agent and the oracle, then the agent will collect a lot of new information about the visual world, right? And then based on this new information, it will update its own visual system to recognize this new concept from the images. And then we provide multiple environment. We assume that the agent can walk inside the living room and maybe the bedroom, maybe the kitchen, etc. So we provide multiple environment to the agent, and then it will gradually collect more information about the whole environment and then update its own visual system. But the problem is that, so we need to enable the agent to the curiosity, right, to learn to ask questions. So here, this means that, okay, we need to have the question policy. This question policy is based on what it knows, what it already knows, and what it has not yet known about the visual world. And then this question policy will help the agent to ask different questions to the oracle side. So gradually we want to train this visual system and also the question policy to improve both of them, so that the agent can have their kind of curiosity ability, and then this curiosity ability can be adapted to new visual system and also new environment. So based on this motivation, we design a architecture for the agent like this. As you can see here, given an image with the same content to the agent and the oracle or human, the agent should have the visual system. Maybe it's just a multiple layers of convolution network, and then it has a graph memory. So this memory maintains the status about, okay, what it already knows and what it does not know yet about the visual world. And then there is a question generator. This question generator is trying to generate some understandable questions to the oracle side. And finally, once the agent asks questions to the human provides an answer to the agent will update its own graph memory and also the visual system to finish the whole loop, interaction loop between itself and the human. So let's first briefly introduce the visual system. So as I just mentioned, the visual system is pretty simple. So it's just a convolutional neural network. So this convolutional neural network will understand the object in the image. For example, given this image, there are multiple objects inside the image. So this visual system will try to recognize its object category, its attribute, and also its relationship, the relationships between different objects. Here, we mainly focus on the spatial relationship, for example, in the front, so behind, on the left side, on the right side, etc. So this visual system at beginning actually is very poor. So maybe it cannot even recognize any of the object in the image. So as I just mentioned, there are attribute distributions and there are spatial relationships between the object, which is represented by the edges between the nodes. So on the other hand, there are graph memory. The graph memory actually stores the information about the visual world. This information actually from two different sources. The first source is from the visual system. So what the agent already knows can help to fill this kind of graph memory. And on the other hand, so as we illustrated, so on the other hand, this graph memory will gather the information from the human, from the oracle, based on the answers provided by the oracle. So you can see here, the visual graph will be used to update this kind of graph memory. And on the other hand, the memory graph, the memory graph will be also updated by digesting the answers from the oracle side. So to summarize, these two kind of updating, we call it top-down update or bottom-up update. So finally, as you can see here, this whole architecture will enable the agent to interact with a human through their language. And this whole agent has ability to ask questions to the human. And then we can leverage this kind of so-called curiosity ability to enable the agent to get a better visual understanding about the visual world. So finally, I would like to also briefly cover the question generator. So the question generator is kind of templated question generator. It takes multiple input. The first input, the graph memory. So this graph memory is just store the information about the visual world, and then there is a sequence of the previous question and answer pairs. So this history helps the agent to decide, what it has already asked about, right? And then it will further ask about new things instead of just repeating, asking the same questions. Then in this case, maybe the human oracle will get annoyed. So and then based on this input, it will output three things. The first is a target object. So which means that which target object you want to ask about in the image, and also the target attribute. So what kind of attribute you want to ask about the object. For example, it will probably ask about the color, about the shape, about the material, etc. And finally, whether it want to use some reference object, because these reference objects at some point or at some time is important, so that to mitigate the ambiguity to the oracle. Because let's imagine, okay, in the image, there are multiple sphere or multiple system object. And then when we ask, okay, well, what is an object? Then this kind of question actually is very ambiguous to the oracle. So let's use an example to showcase this process. So let's say we have some kind of graph memory as shown on the right side. We have the observation, the visual observation on the left side. And at the beginning, the graph memory actually only know a little bit things based on the very poor visual system. For example, it can only know, okay, this there is a pink and a small cube, something like that. And it can only know, okay, the color is red, the size is large, but the shape is not known yet. Then the agent will ask a question like, okay, so the target object is 1. I want to ask about this target object, and I want to ask about, okay, I want to know about the shape of this object. And then the agent will generate a question like, what is the shape of the front most large object? And then the oracle will help to answer this question. And after that, the agent will further ask another question about this object for this color of the metal cube on the left side of the small object.
Question about this graph. Is this graph is the structure of this graph is predefined?
So actually, you can imagine here at the beginning actually is a fully connected graph. So let's say this, we only assume that, okay, this object bound box is provided by before this kind of process. So we have a perfect localization network to localize all of the object in the image. And then, so this graph actually at the beginning is a fully connected graph. And this graph, the edges in this graph actually describe the relationship between each pair of objects. Yeah.
Okay, sure, thanks.
Yeah. Yeah, so finally, okay, so it will get to know one of the objects in the image. So the oracle question answering side, as I just mentioned, so the human actually is very, the humans is not that easy to have a human to answer one of the questions, because we need to keep the human in the loop continuously. But what if we can replace the human, the real human, with the oracle? So this oracle need to assume that this oracle understands one of the things, right? So it understands, okay, the color, the size, the shape, and the material, etc. So once it gives the question like, what is the color of the frontmost object? So it will answer, okay, it's red, because indeed, okay, so the oracle can understand the agent is asking about this object. And indeed, the oracle knows, okay, the color is red, then it will provide answer red. And what is the shape of the object left of the green object? Then this green object does not exist in the image, right? Because the oracle cannot find any green object in the image. Then in this case, okay, the oracle will provide an answer, okay, your answer, oh sorry, your question is invalid. And in other case, what is color of the small object, small cube? But here there are multiple small cubes. So in this case, the oracle will provide an answer, okay, your question is ambiguous. So this kind of different type of answers will help the agent to know, okay, whether the current question is valid or not valid, whether it's ambiguous or not ambiguous. So based on the whole process, we propose 2 losses to train the whole system. Because in the whole architecture, in the whole pipeline, we need to choose 2 things. So first is the visual system. The second is the policy. So for the visual system, actually, it's pretty simple to train this whole system. So imagine we have the graph memory, right? This graph memory gets the information from the interaction between the agent and the human or oracle. And then based on this graph memory, it will leverage a cross-entropy loss between the graph memory and the visual prediction over what images, object, and attribute to optimize the parameters in the visual system. So it's pretty simple to do this. On the other hand, there is a question policy. This question policy actually is trying to ask informative questions to the article. So what does the informative means? So it means that at each step, it will gather some more information about the visual world, right? So here we measure the graph similarity between the memory graph and the article graph. So ideally, we want the agent to ask as less as possible the questions to gather as more as possible information about the visual world. So in other words, the agent needs to quickly complete the memory graph approaching to the article graph. So we use A2C to update the policy after each episode based on all rounds of the interactions on all of the images. So finally, we want to have a questional policy that asking ambiguous informative question and also improve the visual system as quickly as possible. So for the experiment, so we propose 3 different environments. The first environment, just 2 environments. The first environment is a synthesized data set. So if you know, there's a clever data set, and it's just a synthesized data set based on Blender. And the second data set is a realistic data set. This realistic data set is trying to verify whether our learned so-called curiosity can be directly adapted to the realistic environment, knowing that we do not train our model on this realistic data set. So we also compare our method with some heuristic baselines. So there are some baselines like random. So if the agent just random ask any kind of questions about the visual world. And there are other methods like entropy based. We have the agent to ask the questions about the object which has the highest entropy. And we also have another baseline combining the entropy and the context, which means that we not only based on the entropy and also based on the context, the spatial relationship between different objects. So basically, we compare our method with these 3 different baselines, and we have a standard training setting. This standard training setting covers the shapes, colors, material size, and in each image, it contains usually 5 to 10 objects. And for the training, we have 900 training images. For validation and the test, it's 300 and 600 respectively. So the first metric we want to use is the graph recovery. So as we just mentioned, so we want the agent to recover the graph memory as soon as possible. So we check at each round of the dialogue interaction. So how much graph knowledge it has recovered from the interactions. So we check, what if what's a recovery at the round 10, round 20, and the finally the round 50. So we set the maximum interaction round to be 50 for the interactions. So this is the experimental results. So we have the standard training and the standard testing, which means that we the attribute and one of the object category are the same between the training and the testing, but the images content are totally different. So in this case, we compare our method with 3 baselines. The first baseline is a random. So as you can see here, the recovery somehow is not that bad, but it's not as that good as well. So if we use the entropy-based method, it slightly improves the performance over the random policy. And then if we use entropy plus a context, it will further improve the performance. And finally, if we enable the agent to have some kind of curiosity to know, what kind of question it needs to ask about the visual world to better understand the visual world. So in this case, we can see here it consistently improve over one of the baselines. So especially as you can see here, finally if the agent finished one of the interaction round with a human, the proof performance are significantly improved. So we also investigate what if we do not update the visual system during the round of the interactions. In this case, the visual system are always the same at the beginning. And in this case, the graph memory are only updated based on the interaction from the humans. So you can imagine there's only top-down update from the interaction between them, but there is no bottom-up update from the visual system because the visual system is totally randomly initialized and it does not provide any information. So in this case, as you can see here, if we fix the visual system to be random initialized one, in this case, the recovery actually degrade significantly, which is pretty reasonable because you can imagine that the agent at the beginning know nothing, and if it's always know nothing, even if it cannot learn from the knowledge gathered from the interactions, then okay, it will be definitely dumber than the agent, which can gradually learn its own visual system, and this visual system can be generalized to the new object, to the new images, right? So you can imagine that this knowledge actually has been learned in the agent itself. So next we examine, what the agent can act in the novel object environment. By novel, I mean, there are new colors or shape. So if you remember, this kind of colors or the shape actually do not exist in the training set. And also we examine, what if there are some mixture between the novel and standard color and shapes? And finally, we examine the model, the agent in the realistic scenarios. So based on this, we evaluate the performance. First, the standard training, standard testing. This is the performance. And then we examine the standard training but novel testing. As you can see here, actually, the performance actually does not degrade much, which means that the agent can generalize very well from the standard training domain to the novel testing domain. And also there are some mixture between the standard domain and the novel domain, then still it's pretty robust to these scenarios. And finally, we directly test our learned policy on the risk scenarios. This risk scenarios actually is very, very different from the synthetic dataset, right? So, but still, it seems like, the agent can perform pretty well in these new scenarios, even, the images are totally realistic and the scenario are much more complex than the synthetic dataset. So this is example. So knowing that, there is no training on these realistic images, right? So, and then at the beginning, the agent will ask what material is the leftmost thing. The answer will be, food. And then there is a leftmost object, what is it? It's a potato. And the leftmost object is what color? And it's brown. And gradually, it will ask about their plastic ball in the middle, and it's paper and etc. Finally, it will ask about more and more things in the images. But you can see here that these questions actually are pretty informative, so that the oracle or the human can directly answer one of these questions. So there are some, finally, so I did not show more results, but for the interest of time, maybe I just show this sample. But if you are curious about more examples of visualization, so we can talk about offline. So to summarize with this work, so there are three main takeaway messages. So the first is that we propose to learn this kind of visual curiosity for agent through the language interactions with a human. So there are multiple round of interactions between the agent and the human. The agent will ask questions to the human, and the human will provide the information to the agent so that it can learn from these informations to update its own visual system. So through the interaction with human, the agent improved the visual understanding capacity on the novel concept gradually. And I would say this is very similar to the curiosity I mentioned at the beginning, the example. So at the beginning, okay, a child may not know something about the environment. For example, there is a cup, there is a toy, and at the beginning, it cannot know, okay, what kind of concept, what does it mean? Then it will, he or she will ask about, okay, the object to the parent. So finally, we testified that this learned question generation policy can directly adapt from synthetic data to realistic data set. I think this is very important. So because our own kind of the curiosity actually, our own curiosity can be used in different kind of scenarios, right? So if we move to another place, we still have this kind of ability to understand what we know and what we do not know. And we only want to ask about the question, ask questions about the unknown things to others, right? So basically, we do not want to, ourselves, we do not link this kind of curiosity from one experiment to another experiment. So this is what we do not want. So this generalization ability is very important for an agent curiosity as well. So after talking about the learning visual curiosity through the language interaction with humans, so I would like to also introduce the learning visual curiosity by moving in 3D environment. So in this work, we want to enable the agent to have the ability to learn to move inside the environment to understand an object. So you
sorry.
Oh yeah.
Yeah, I have a quick question for the previous work.
Yeah.
So in the so when the agent is asking a question, gets an answer. Let's say he asks, "What is this large red object?" I'm referring to the Clever dataset, and the answer is a cube.
Yeah.
Does this information transfer to other objects in the graph? Like, do you have like a kind of a refinement of your knowledge?
Yeah.
Okay, so I guess I missed that. Okay, cool.
Yeah, there is a graph memory. So in the agent system, so this graph memory will maintain the knowledge, the global knowledge about the image, and this global knowledge will be updated from two different ways: the top down, based on from the interaction with the human, and the bottom up, if the agent update the visual system through observing multiple images, it will probably understand some novel object based on the training, based on the learning from another image, right? In this case, the visual system can also update the graph memory based on its own learned visual system. So yeah, so basically, yeah,
okay.
Yeah.
Perfect, thanks.
Yeah, thank you. Okay, so let's move to the second work. The second work is trying to enable the agent to have the curiosity, so-called curiosity ability to move around the object to understand it. So let's imagine a scenario like this. The input for the object for the agent is like, okay, there is the object like sofa. Even we understand it. Maybe the agent at the beginning does not understand. Okay, it's a sofa. It's a white sofa, something like that. So based on this, the agent will probably want to move around the object to see more part of the object, to move again and again. Oh, finally it's recognized. Oh, it's a sofa, and it's a shape. It's something like this. So this is basically the motivation we want to do this work, because as humans, we have the ability to understand the object by move around the object, by manipulate around the object, right? So maybe at one viewpoint, we do not recognize this object, but maybe from different point of view, we get more information, then we finally understand, oh, it's a sofa, or it's some object. So I think this is very natural transition from our humans to the agent. So based on this motivation, we propose embodied and model recognition. So as you can see here, there is a passive pipeline shown on the left side. The passive pipeline is just, okay, take a region and take a region, and then there's a model recognition, and then it will recognize, okay, it's a sofa. But probably it can't recognize very well because it's just take one viewpoint from the object. Maybe there are a lot of occlusions. Maybe the other kind of viewpoint is better for the agent to understand. Then we propose an embodied kind of a model recognition system. So this system consists of two main components. The model recognition part is identical to the model recognition part in the passive system, but it will also have the action policy, which guide the agent to move around the object to understand the object better. So this kind of two together can enable the so-called agent curiosity in the 3D environment to understand the visual object. So to benchmark this kind of ability, so we propose 3 subtasks. The first task is object recognition. The second task is 2D and model localization and the 2D and model segmentation. So this way, the agent will globally understand, okay, what's the concept of this object, and also what's the overall shape of the object. By a model, it means that, so it will recover the occluded part for that object, not just, okay, the visible part for the object. So we also simplify the scenario as well. So we just, okay, assume that at the beginning, the agent want to understand some specified object. For example, in this image, there are multiple objects in the image, but the agent will be asked to understand this object noted by this red box at the beginning. And then it will only predict for the first frame. But of course, the object recognition actually is agnostic to different frames. But the 2D and model localization and 2D and model segmentation actually is for the first frame. This way, we can simplify the task a little bit so that, okay, we can benchmark our model on the standard way. So there are some distinctions to the related task I would like to emphasize. The first is the visual navigation. So the visual navigation assume that, okay, the agent want to go to some places. So for example, from the living room to the bedroom, right, or to the kitchen. But this is more like, okay, it's not just find an object, understand an object. It's more like, okay, it's want to search some object or some scene in the environment. So the second is a video understanding. So the video understanding is more like, okay, it's given a video sequence, it want to recognize, okay, an object or a scene. But still, this kind of video understanding actually cannot be used to, cannot enable the agent to explore in the 3D environment because there is no interactions between the agent and the video. So we cannot manipulate that video, right? So I want to distinct these two tasks, visual navigation and visual understanding, from our embodied and model recognition task a little bit. And to further highlight, so I would like to mention that you can imagine this kind of task to be the last mile problem for the agent navigation. So let's say, okay, if we want to ask the agent to find a bottle, find a cup in the kitchen for us, and then it will probably first navigate to the kitchen, and then it will localize an object which looks like a cup, and it will gradually, okay, move around the object to recognize, oh, it's a cup, or maybe it's not a cup, and finally to move to another place. So basically, yeah, so I would like to position this kind of task to compare with this, compare it with the other tasks like the visual navigation and the visual understanding. So the UVR model is pretty simple, as I already showed previously. So it contains two components. The model recognition part is kind of convolutional neural networks, and the action policy is another neural network with action predictions. So the model recognition part is kind of sequential model. It's based on the convolutional GRU to take multiple frames as input, which are gathered based on the actions of the agent, and then it gradually predict the output. For example, at the beginning, maybe it's pretty poor because it just get one frame, and this frame is not enough to understand the object, and it will predict incorrectly, like so far. And gradually it will get more information about this object. Finally, it will understand, oh, it's a child, not a sofa. So learn to move policy part is also consist of a sequential model. So it will take the visual representation from each of the frame, and then also append some kind of history information from last step. For example, it will invert the last action step, and then concatenate this action information and the current visual information together to predict the action step for the next for the next step. So basically, these two are all a sequential model, but the output of these two parts is totally different. The first part is to recognize it from three different perspectives: the concept, the shape, and the localization. And the second part is predict the action. So here we have multiple discrete actions for the agent. But the dataset we collect is based on the HOS 3D. Unfortunately, HOS 3D actually are now available anymore because of their legal issue. So based on this HOS 3D dataset, we collect multiple object categories like bed, chair, desk, dresser, fridge, sofa, etc. And we'll also categorize each of the category into two difficulty levels: the easy level and the hard level. By the difficulty level, it mainly depends on how many occlusions it has at the beginning. For example, maybe the occlusion is very, very huge, and then it's be very hard for the agent to get to know how to move to understand it. So as you can see, we also have a baseline based on the shortest path. So we, based on the 3D configuration, we run an algorithm to find the shortest path to approach the target object. So the results are shown here. So we compare with different methods. So the SP means shortest path, and the AP means active path, something like that. And then as you can see here, we compare with multiple shortest path baseline, and we also compare. We also report the performance for our active paths in the environment. So with the action step going, the recognition accuracy are gradually improved, and this model box AOU are also improved gradually, and again the model mask are also improved with the action steps. So which means that embodiment helps to improve the visual recognition performance, and our learned movement policy actually for outperforms the other moving policy like the shortest path and other combinations. So finally, it seems like the model recognition performance tends to saturate at the end of moving. So we assume that we hypothesize that so this is because maybe it does not need to so much steps to recover the information, because maybe it can just use 3 or 4 steps to gather all of the useful information. And again, so as you can see here, so our proposed policy actually can help the agent to more quickly to gather information. And sometimes even the shortest path policy can hurt the performance if to move further and further. So the other application study based on our model. So we try to use different feature aggregation and also different feature open method to aggregate the information from different frames. So as you can see here, GRU works much better than average or max pooling over multiple frames for the aggregation. And warping the feature for different frames for the aggregation use optic flow helps to improve the performance. And finally, combine the GRU and the optic flow works slightly better than either. So you can see this is prevalent. So finally it will get better performance than other kind of a method. So finally, we inspect what kind of actions the agent learns during the training. So we compare the active path with the shortest path based on which action step, which action it select at each step. So for example, there are multiple actions: go forward, turn left, turn right, and then go backward, something like that. And then, as you can see here, the distribution between distribution of the shortest path and the active path actually are very different. On the right side, we also examine, what's the distance between the agent and the object. So as you can see here, the shortest path will always decrease the distance between the agent and the object because, we are using the shortest path to move towards the object. But our active path actually is slightly different in terms of the pattern. So it even gradually increase its distance between itself and the object. So you can see here this pattern actually are very different, and which also explain the difference of in terms of the performance as well. So finally, I would like to choose some simple visualization result. As you can see here, this is an initial input, and then for the passive one, it's just predict something like this. But for the active one, it will learn to move a little bit left the viewpoint, and then it will get better understanding about the object. So this is the shortest path one. So it will get close to the object, and gradually it will update the performance as well. Of course, this shortest path seems like works better than the passive one, which just use a single frame, single image to predict. But here, if we enable the agent to actively move towards the object, maybe it does not need to move towards the object. It's just move surround the object. So as you can see here, so this is the shortest path, and this is active path. You can see here it does not need to move forward the object. It maybe move to the right side of the object, and then get understand the right part which was included at the beginning. So that's here. So there are some takeaway messages. So based on this work, we showed that embodied visual recognition systems actually can help the agent to have the ability, to know how to move around the object to get a better understanding. So of course, we have shown that this learned embodiment curiosity actually helps to get better visual recognition about the object than, for example, the passive one, also than the shortest path one. So again, we still found learning a better moving strategy actually is pretty challenging, but it's indeed helpful to improve the visual indication. By challenging, I mean, so at the beginning, we imagine an even more complex task for us. So finally, we found it's pretty hard to train the visual recognition part and the policy part if we want to have more complex task. And finally, we simplify the task to only predict the first frame, about the concept, about the localization, about the mask, and we make it work. And then, so as you can see from the slides. To summarize these two works, I would like to further recap the motivation for these two works. So the motivation is pretty simple. So we want to convert the visual system to a visual agent, which can interact with human through language and interact with the environment through embodiment or actions. But here we particularly are interested in the so-called curiosity for the agent. So that's why I put the one directional arrow from the humans to the agent, from the environment to the actions. The visual agent in this case need to ask questions to the human so that the information flow from the human to the visual agent, so that the environment, the information flow from the environment to the agent. So this is basically what we have already covered in these slides. So the so-called curiosity for the visual agent. And on the other hand, I would like to emphasize that the visual agent not only need this kind of visual curiosity to learn from the humans and the environment, but also it needs to be beneficial to the human and the environment. So that's why I put another directional arrow from the visual agent to humans. For example, the visual agent, once the visual agent understands the world, so it probably can help the humans to finish some task. For example, gather, put some, as a robot, we probably want to ask the robot, okay, to help us to deliver something, or maybe it can even teach the human children as a teacher, right? So basically, this is very interesting to explore. And on the other hand, the visual agent need to also help to manipulate in the environment. For example, grasp a cup or some other things once it knows about this object, the shape, the material, the other property about the object. Then we probably need the agent to interact to manipulate the object as well. But again, so there are a lot of challenging problems behind this kind of hopes. So for example, between the human and the visual agent, so how we can enable the grounding of the language to the visual world. So based on the question, I cannot remember the name, but based on the question asked at the beginning, okay, so we assume the agent already localized one of the object, which means that actually we already assume that the grounding actually is partially solved between the visual object and the language. But in the realistic case, actually, it's much harder because we do not have the perfect localization network to localize the object for the agent. So how we can make the whole network, whole system interpretable? This is also very important because we want the agent to interact with the human friendly, fluently. And finally, we want to enable some kind of reasoning ability for the visual agent. So on the other hand, with the environment, so there are a lot of different things we want to explore in the future. One of the things is that, okay, it's just kind of sim to real. So even though we show that our embodiment curiosity for the agent can be successfully transferred from the synthetic data to the real world, but still it's very toy because it has a perfect localization, and also it has the very simple concept in the benchmark. So how we can enable an open world, and how we can enable a faster adaptation from one environment to another environment is still open question and also very challenging questions. Yeah. So yeah, so that's it. So I think, yeah, I would like to end up here, and welcome to have any questions. Yeah, thank you.
Thank you so much for a great presentation. That was really impressive. So does anyone has any questions? I think we just lost some people on the way. That's probably like getting a little bit late on the end in Europe and probably in Asia.
Yeah.
So and yeah, Mark is going to. I think everyone also needs to leave for another meeting. So just because we're still recording, and I hope people will watch that. So I have just kind of one question in this respect, a little bit on the side of the research. How do you think IGLU can help with this all great research directions which you mentioned, especially in the end of your presentation?
Yeah, I think this really an open question to me. So as I mentioned in this slide, so I would see the IGLU is something like this domain, right? So basically, okay, there is a visual world like the environment in the IGLU, and then okay, the agent. In this case, in our work, actually, we have two roles, the agent and the human or oracles. But in IGLU, actually, similarly, there are also two roles, right? The builder and the instructor. Yeah. So I would imagine this is very similar. So, but the task is different. And also, I would imagine that in this IGLU task, the builder and the instructor should also have some essential ability. For example, how it can ground, the grounding ability, and the ability to ask clarification questions from the builder to the instructor as well. So I would imagine that this kind of task can help us to build a real interaction, in real interaction between these two roles. So because here in our work actually is just one directional. So there is no question like, okay, asked by humans to the agent. Maybe the question is ambiguous. And then the humans may be probably able to ask questions to the to the agent to resolve this ambiguity, but here it's missed. But in the IGLU, actually, I would imagine the ideal case is that, okay, the builder and the instructor can answer question, can ask the questions to each other mutually. So this would be very exciting. So, and also the task itself is much more challenging and more interesting than the scenario I just described, because in that case, just understand the object itself, just a very low level concept understanding. But in the IGLU, I think it's much harder. So it's needed to, okay, manipulate, it needed to recognize the object and also manipulate the environment as well. So that's would be very interesting to explore. Yeah.
Thank you so much. Thanks for your presentation. Yeah. And yeah, talk to you soon then.
Yeah, thank you. Thank you for the invitation, Julia. Yeah, thank you very much.